LeChatelier's principle states that an equilibrium system will adjust to relieve stress applied to it. As an example, take the system in which nitrogen and hydrogen react to form ammonia. Now, this system might be at equilibrium, or equilibrium already, in which the partial pressures of hydrogen, ammonia, and nitrogen are no longer changing versus time. However, if you inject hydrogen at a given moment, that will increase the concentration of hydrogen. Now, the system will adjust to relieve that stress, so it will often do what is opposite of what you did to it. So, by your injecting hydrogen, it will relieve the stress of injecting this hydrogen by removing some hydrogen. Soon, though you increased its concentration, the system will respond by decreasing the concentration of that hydrogen. And at the same time, as hydrogen is being used up, as the reaction is proceeding to the right, the concentration of ammonia, the product, will increase, and the concentration of the other reactant, nitrogen, will decrease. Until eventually equilibrium is reestablished, where you have concentrations or pressures of products and reactants which are no longer changing. Now, the reason that the system will relieve this stress is that though you had the system at equilibrium, by injecting hydrogen, you'll be increasing the concentration or pressure of this reactant. Now, by doing that, by increasing the concentration or pressure of a reactant, you will decrease the value of the reaction quotient, Q, to the point where Q is now less than K. Now, we know that the system will continually adjust until Q is equal to K. And so Q must increase to become equal to K. So in order for Q to increase, the pressures of the products will have to increase, and the pressures of the reactants will have to decrease. Now, one way of viewing this, besides comparing Q versus K, is to take a look at a bucket full of water. So you have a bucket full of water. Now, if you were to inject reactants, if you were to add reactants to the left side, for a brief moment, there would be more on the left than the right. So, considering we have water here, there would be a higher height of water on the left than the right. However, the system will readjust to reduce that stress, and so it will shift water from the left to the right until a point of equilibrium is reached again, where the amounts of water on the left and right are no longer changing. Similarly, if you were to remove reactants, if you were to scoop some water out of a bucket, say, then water would have to flow from the right to the left. And that would occur until there would be a new height of your water and a re-established equilibrium. So our water is a lot like the reaction system, in which by having the water flow to the left, what we're really saying is that the reaction shifts to the left. So some product is soon going to turn into reactant. Now, there are large kind of numbers of types of cases here. We saw that by injecting hydrogen, that might briefly increase the concentration of hydrogen, but soon the system would respond by pouring water on the left. You shift the reaction to the right. The system would respond by having its reactants turn into new additional products. And so the concentration of nitrogen and hydrogen would decrease, and the concentration of ammonia would increase. You add this reactant, and the system will respond to that stress by getting rid of that reactant and shifting the reaction to the right, so that more reactants turn into product over some time. Now, at the same time, this will also be supplying heat, as this is an exothermic process, and so it would increase the temperature. However, the equilibrium constant, disregarding this change in temperature, if you were at constant temperature, that equilibrium constant would not change. Now, by removing hydrogen, by removing some of this reactant, the reaction would have to shift to the left to respond to that removal. And so that would turn some of your product into reactant, increasing the concentrations of your reactants and decreasing the concentration of your product. If you were to inject ammonia instead, inject this product, the system would respond to this increase in the concentration of ammonia by decreasing the concentration of ammonia. By pouring water onto the right side of a bucket, water will soon flow to the left. So that will shift the reaction to the left, increase reaction concentrations, decrease product. How about adjusting the temperature, just deliberately, without affecting anything else? By adjusting the temperature, by increasing the temperature, this will make the availability of heat increase. Increasing the temperature increases the amount of available heat. This is just like adding a product. This will shift the reaction to the left. By increasing the temperature, that shifts the reaction to the left, increasing the amount of reactants, decreasing the amount of products. Now, this is the only case in which the equilibrium constant will be affected. Now, by increasing the temperature, we saw that the concentrations of products decreased and the concentrations of reactants increased. Decreasing products and increasing reactants decreases the product over reactant ratio, or the equilibrium constant. So the equilibrium constant, the effect of increasing temperature on it, differs depending upon whether you had an exo or endothermic process. So in this process, where we had an exothermic process, increasing the temperature increased the equilibrium constant. However, if you were to have an endothermic process, increasing the temperature would decrease the equilibrium constant. So it really depends upon what type of reaction it is that you're dealing with, whether heat is on the right or the left of the reaction. How about decreasing the volume of this container full of gas? By decreasing the volume of the container full of gas, that will increase the pressure of the system. Now, increasing the pressure of the system, it occurs for both your product, ammonia, and also your nitrogen and reactant and hydrogen reactants. Now, increasing these pressures has different effects on the numerator versus the denominator side of this equilibrium constant. You see that by increasing the pressures of this reactant, which is squared, versus the combination of that product, which is squared, versus the combination of our reactants, which are ultimately 1 times 4 cubes, 1 plus 3, or actually to the fourth power, we see that Q ultimately becomes greater. That happens because, we see that by increasing the denominator more than the numerator, that actually makes the value of Q decrease. So that soon Q is less than K. And having Q less than K, then Q will soon need to increase until it's equal to K. And that can only happen by increasing the amount of products and decreasing the amount of reactants. Another way to view this topic, though, is to say that by your increasing the pressure of the system will respond to that stress. If you increase the pressure of the system will decrease the pressure of the system by decreasing the number of gas particles. So we see that we have all gas particles here, and this is important. You have to pay attention to the states of matter here. But we have 4 gas particles on the left, and we have 2 gas particles on the right. By our increasing the pressure, the system will tend to decrease the pressure by decreasing the number of gas particles, turning 4 particles into 2. 4 particles into 2. So that will shift the reaction to the right. And instead of volume being discussed, perhaps the pressure might be discussed. Say that we were told that we decrease the pressure of the system by implication by increasing the volume, then we would have all the opposite effects. What if, however, we were to increase the pressure of the system by adding helium? Helium would have no effect on the equilibrium system, because helium is not in our equilibrium constant expression. Helium is nowhere present in this, and so it would have no effect. It is an inert gas. However, what if you were to add oxygen gas? Well, oxygen gas is a little different because it can react with this hydrogen at this very high temperature and produce water. And so by adding oxygen, that consumes the hydrogen and hence is like removing the hydrogen from the system. That would shift the reaction to the left. Finally, adding a catalyst. Now, this actually has no effect on the equilibrium system. Catalysts are able to increase the reaction rates in both the forward and reverse directions, but they're not able to affect the concentrations of products versus reactants at equilibrium. You see that whereas normally, before adding catalysts, it's a slow reaction from left to right, and it's an even slower reaction from right to left. But by adding catalyst, you make it easier for the left to right reaction to occur. There's a lower activation energy barrier, but also there's a lower activation energy barrier going from right to left. And so both left to right and right to left reactions are affected, and so there's no overall change, though, in the relative amount of enthalpy of our reactants versus products. And having no change between the relative enthalpy between reactions and products, having no change in the heat of the reaction, there is no effect on the equilibrium constant at all. Thanks for watching, guys.